I rewrote it, but I don't know if I can transfer it over to that. Yeah, I can try to use it. So what happened is, we came down to, let me just go back and maybe if I can just put my file here, it will be easier and not bother you with the other things here today. Let me do that. Yes, do this. So let me put this file here. Just change the file. Copy. Paste. So. So I change the file just to replace the file in this image. Okay. Yes, this is it. Okay. Have we eject this? Anybody who's good at this?
What?
Ejecting.
Eject?
Yeah. I want to eject the flash.
The flash drive out.
Has to be done.
Get done. Well, you have to go to my computer.
Okay, I don't know. I don't use Windows. So. Oh, okay. Yeah.
This is the flash drive which you like?
Yeah, some of them. I can just take it out.
Yeah. Yeah, right.
You shouldn't do that, but it's okay. From time to time, it's okay.
Use your coffee.
So let's see what we. First of all, let me go back to this problem I told you about. So it's an exercise that was a little bit out of the blue. I was so we can come back to this. So I asked you to prove that if this is non-negative for all directions, then the function is one-dimensional. Then, of course, it's constant because you just take the reverse direction and it becomes 0. So this was not the case of the questions. So the question itself was not wrong, and the answer is that it's going to be actually constant, which is one-dimensional. But my intention was not this. So here is the question for you. So suppose for any direction E, we have directional derivative of this function does not change sign. Does not change sign. Let's say alright. Of course. Doesn't really matter, sorry, I don't know, but then F is one-dimensional. Okay, so this is the correct question. It is not what I wrote yesterday, it was not what I meant. So try to show this. So let's go back to where we finished. And the proof, I started with a little bit of flows, so I changed it yesterday evening to actually a proof which is simpler. Yes, so let me go through it completely so we can see. Okay, you have the conclusion that any blow-up limit is homogeneous of degree 2. Do you recall that part? Where we use the monotonicity formula, the Weiss monotonicity formula, and from that we see that once you put RS here, two different values, and then one of them go to 0, of course then the product will go to 0, so you get this one. And rescaling, you get that the limit is going to be the blow up, the monotonicity formula of the blow up. But then it's constant, so we realize that the derivative should be always strictly positive unless the function is homogeneous of degree 2. So therefore, U 0 must be homogeneous of degree 2 because the value is constant. So that was the proof of it. And then from here, we want to go further and where is it working? I think it is the stick. You forgot the stick. Huh? I think there's a stick you should have. Yeah. So, where is the stick?
Is it?
Oh, okay, inside. Okay, now it should work. Thank you. So the next one was so any blow up of homogeneous function of degree 2, and our next claim is So I want to prove basically convexity from it, and then we'll actually get polynomial one-dimensional function, or it's a polynomial. So let's see how it works. So the solution would be something like this, or it will be a polynomial. This is sort of half polynomial. Okay, so this is changed finally. Laplacian of U0 is 1. Yeah. So if the set has empty interior, that's one scenario. The set has empty interior. Then we realize that Laplacian of U0 is going to be 1 almost everywhere. Because the free boundary has measure 0, so we can just ignore that. And there's no interior, so that's it, nothing is there for the Lebesgue measure. So Laplacian of u, there is actually one, and then Liouville's theorem applies, and you get a polynomial. I hope you work this out. So if Laplace of u0 is 1, everywhere the function has quadratic growth, observe the function has quadratic growth, then the function has to be a polynomial of degree 2. Alright? So the second case that was a little bit more complicated, we proved through a so-called ACF monotonicity formula on the board. That's one way, but I'm going to do it a little bit differently now, without using ACF. Because you realize that ACF can, in general, not be used in all PDEs if you have a different type of PDE than the Laplacian. So you might still want to do it. So we start proving convexity, and from the convexity we can later on prove that the solution has to be... This proof is longer, actually, a little bit more involved than the monotonicity one. But still, it doesn't use heavy machinery. It's a little bit... It uses mostly classical analysis. So we try to prove convexity first. Convexity is already good. Okay, so we want to prove that any global solution U0 is convex. This is actually not necessarily only blow-up solutions, but generally global solutions, which of course have quadratic growth. They will be convex. Okay, so what we did yesterday, we know already that second derivative is bounded. So let's say bounded from below by constant minus c. So there is an infinite value for this. So the second derivative of this has an infinite value, we call it minus m. There must be a sequence that converge to the minimum or infinite value. Let us scale it. So we did scaling, we took these points, we're sort of wandering around, and then they go to either boundary or they go to infinity. What you do, you scale it, you take it and you scale to the boundary, and you make it, if it's small, you make it bigger, if it's huge, you make it smaller. Depends on what dj is. If dj is less than 1, you scale it to 1. If it's much larger than 1, you scale it back to 1. So the idea is to bring down all the time xj to center origin. Shift it. I always get this allergy in the mornings. It was very smoggy today. I thought it was fog, smog.
It's small.
Smog, yeah. So Laplacian of Vj is 1 in the Borel rate is 1. Vj is uniformly bounded due to quadratic growth. And therefore, subsequence, according to all the rules we have learned, compactness, will converge to a limit solution, where Laplacian of V0 is 1 in B1, and not only there, but it's 1, of course, everywhere where its support is. And then you really take the values, the infinite values for this guy at the origin. But then, by minimum principle, this cannot happen. This function has to be exactly minus m constant. So second derivative in this direction is constant, and then we will prove that this cannot happen if V0 is coming from the PD that we're talking about. So take that connected component when this happens. It doesn't necessarily have to happen everywhere, but there is a connected component. It must be other component. Could be other components, something else happens, I don't care. So what we do, if there is a component when this happens, at least one of those components, which contains the B1, then we just ignore the rest. We can actually redefine the function, consider it 0 outside. Okay? So, because that's what I'm going to use, so think about it. That this is one component, this is another component. So here is B1. So my function here is V0 is minus m here, but not necessarily here. The minimum principle only applies to the connected component, not everywhere. There might be another component here. So what I do, I just ignore this part. So this is, let's say, omega 0. So I redefine V0, let's call it something else, W0. I will not call it W0, but so I can just work here, and then the function is 0 here. So I again redefine it and call it V0. Redefine W0 with the name that you relabel it and call it V0. Okay? So let's integrate. So if you integrate, the function is second derivative is minus m. So think that you have direction is E1. So you take integration in the E1 direction. Calculus tells you you take out the first derivatives, you will get minus m times x1 plus a function a of x prime. X prime is the other directions. So x prime doesn't contain x1. It's x2, x3, etc. So the first integration gives you d1 of v0 is minus mx1 plus a function depending on another direction. Agree? I don't know what a is, I don't care. I only know it doesn't depend on x1. Again, integrate. And this will be x1 here, plus another function b of x prime. Okay? I'm not doing anything but calculus 1. So this is the picture, and this holds everywhere in this connected component omega 0. Okay? So this is exactly the scenario I have, and I forget about the rest of the components. So let me erase here and let's see what we get. So what I have is the following. I take a point, call it C, in the set where the function is strictly positive, and then I go along this direction. Then, you see, if I go in this direction x1, this guy becomes larger and larger. And this is just constant. And this guy is also constant. Because x prime is fixed now when I go in this direction. So what happens is that x1 becomes much larger, eventually x1 to power 2 becomes much larger than the linear x1. So after a while, I have to hit a negative value. Okay, so this will become negative, but the function is positive, or non-negative at least. So this is not going to happen. So it means that, and this is only true, that equation, or that equality here, that the value equals to this is only true inside omega 0. It means after a while I'm going to hit the boundary, and then this doesn't continue. So here I have the boundary. So I call this z plus lambda, or t plus, I call it t plus e1. Agree? I'm going to hit a point where the function is 0. This is a free boundary. I take any other point, I hit another point. I can do it on this side as well, and then I get something like this. So here v0 is 0, here v0 is 0. Oh, I don't need all these things, but what happens is, so this is z minus t minus e1. What happens now is my function is, think of a concave function, which is non-negative. The function is 0 here and 0 here, and the function is concave. Because second derivatives, concave, one-dimensional concave. Second derivatives of function d1 is minus m, so it's a concave function. So the picture is like this. But is it possible for this function to be having gradient that is 0 also? That's not possible, but there's actually an easier way. So the function is having a, if you look at the profile of the function, it's something like this. But now, d1, so my function is 0 here, it's 0 here, and also in the rest of the set. And this function looks like minus m x1 plus a of x prime. That's the derivative. You have such a function. When x prime z is fixed here, that's x prime is fixed, and you go along this linear function has to be 0 at 2 points. A linear function cannot be 0 at 2 points. So it means that has to be 0 at 2 points. Call it a z1 and z2 here, or z plus and z minus. But this is not possible. So this is a faster proof than what I tried to do yesterday. And that's it. So you get a contradiction. So that means that the original, or the initial state we assumed m is a positive value is not true. So m is 0, and that means that second derivatives that are minimal is larger than or equal to 0. Okay, so this is the shorter proof. Okay. So what we have done is that we have shown that what have we shown? We have shown that this V0, we have shown that U0 actually, that U0 is convex. So we're in case 2 now. So we have shown that, let me go back just. Yeah, I want to prove that this is non-negative. So I'm assuming it's becoming negative infimo, and then I get a contradiction. So the claim is that this is non-negative. And we have shown that. So we have shown that second derivatives of U0 in any direction is non-negative. So now U0 becomes convex. So now this part is a little bit tricky. So let me do it carefully. It's written in a very without any detailed explanation. So let me do it on the board. The idea is to prove that the function is one-dimensional. The idea is to prove the function is one-dimensional, and now we are at the case when either it's one-dimensional or polynomial. The polynomial case we're done. So if the interior of the coincidence set is empty, the function is polynomial. So if it's not empty, I want to prove it's one-dimensional. And so far, I have proven that my function is starting with a blow-up solution, so it's homogeneous. It's convex and homogeneous. And from convex and homogeneous, I claim it has to be one-dimensional. Now, the picture is like this. The set when U0 is 0 is a convex set. Because U0 is convex, so its level sets become convex. So the 0 level set has to be convex. Okay, that would be an exercise for you maybe. So a convex function has 0 convex level set. So the 0 set is a convex set. It could be bounded, unbounded, I don't know. The function is homogeneous, so it has to be unbounded. So you have a cone like this, well, convex. So a convex cone like this, and homogeneous convex cone, that's the set when you use 0, 0. And this set. Now, you can think of this on the sphere. So there is a set on the sphere which represents this convex set. Okay? If I prove that this set is completely half spherical cap, then I'm done. More or less I'm done, if it's half spherical cap. Now, the scenario is like this. If I take a plane, think two-dimensional. think two-dimensional. So if I take a line like this a supporting line, since this is convex, there's a supporting line, and if the supporting line here coincides with the boundary, then it's a half plane. If it doesn't, then you will have something else also. So is the picture. So here, U0 is positive, completely. Okay? That's the picture if it's not a half plane. If the set when the function is 0 is not a half space, then this is the picture. Now, what I want to do, well, it's sort of explained there, but I don't think that, I don't think that's enough explanation. So what you do, you take a direction. You take any point here and take the direction here like this. Take this direction, call it E. You know that the following happens actually. DE U0 is not negative. Why is that? You start from here, DE U0 is 0, the function is 0, so the derivative is 0 inside at this point, and then you continue, and then I'm claiming that it's going to go positive. Because my function is, because second derivatives are non-negative. So it means that the first derivative of this first derivative is positive. So this guy is increasing. It goes from 0 to be non-negative. And then any point here can be reached by this. So you go in this direction, the function becomes non-negative. This is an important fact. So this function, we call it v or whatever you call it, h. So the function h is what? It is harmonic in the set omega 0, what you want to call it, omega 0, let's say. This is a harmonic function. So a harmonic function which becomes 0 here, so h is 0 here, on the boundary of the cone, then it is non-negative inside, and it's a harmonic function. And the cone has an angle which is less than pi, sort of, in all directions. Well, let's say at least one direction, not all directions. Because it's not completely half plane, half space, so there is at least one direction the cone is having a smaller than pi degree, opening of pi. So what you do, you take a plane, two planes like this, in this direction, and make it one two-dimensional barrier. Okay? You're not used to that, you have to think it like this. So again, the same picture. So you have your cone here. Okay? Now you can think that your plane is like this. Okay? So here you have that Laplacian of h is 0. H is 0 on this boundary. H is that function there. And h is non-negative. There's one more thing we know here. That U0 is C11. So h is C01. H is C01. Now what I can do another play here. I can take a little bit, since this is not completely a plane or a line, I can take a little bit, open it up a little bit. I can open it up a little bit, take another plane, I take a new function, g. So let's say this is my cone K0. I take a new cone, K1, open it up a little bit, And then define a new function g. Define g such that Laplacian of g is 0 in k1. So this is k1 complementary. So let's say this is k0, it's easier. And this is k1. In k1, g is 0 on the boundary of k1. G is harmonic. And then g is homogeneous. You can actually come up with what? Come up with that g is explicit. You can actually have explicit. Two-dimensional. You can use this, we play around with z to power alpha, the real and imaginary part of that. The first day maybe we did that. So we use complex analysis. Take z to power alpha, and then the real or imaginary part, and rotate it correctly. For a certain value of alpha, which is less than 1, because the angle is now more open. Okay, if the angle is small, alpha is larger than 1. If the angle is like this, larger than pi, alpha is less than 1. That's the rule. So what happens is that you get a two-dimensional function, which is a barrier, is larger than, is smaller than, g is smaller than h. This is a very good exercise. It might take you a few good thinking before you can finish it. So g is less than h by barrier argument, because you see g is becoming 0 here. H is already larger than or equal to 0 in this boundary. So maximum principle or comparison principle sort of would tell me that this is the situation. I can make this like this. Of course, you have to play around with the ball and boundary values, a little bit of that, just to make everything correct. G is less than h, but g is close to the origin. G is, when you're very close to the origin, g is like r to power alpha. And alpha is what? Is less than 1. But h is Lipschitz, so h is like r to power 1. And alpha is less than 1. This is not going to happen. This is not true if r is too small. So if you're close to this point, you get in trouble. So this cannot happen. This is a geometric argument, and easy to just derive. But you have to be very careful with the details here. So this tells us that the cone cannot be there. This cone has to be a complete half space. So the conclusion is that the cone has to be a half space somewhere here. Yeah, here. And from there you have that. Okay, well here is the barrier argument. It's very short. I didn't do much in the detail here. So you get a half space solution basically. Okay. Well, there is still one exercise here. So if you have that lambda 0, the coincidence set is a half space, and your function is convex, how do you know that function is one-dimensional? Okay, I'm just claiming it here, but you have to prove it. So here's one exercise. If you have your solution, which is convex, so you have your u0, which is convex, and the set when u0 is 0 is a half space, so it means it contains a complete, let's say upper half space, or lower half space, is completely in the coincidence set. Can you prove that the function is one-dimensional? That's a good exercise. I think we're getting too many exercises. Yeah, we left them mostly like exercises in the book, or so. I mean, this is general knowledge, basically.
So, do you use that it will be a solution here? Do you require to use it as a solution for that particular exercise?
That I don't remember. I have to think about it. And thinking is never good when you're standing in front of people. You have to be prepared. So maybe not.
Also, I have a
No, wait a moment. Because if you have second derivatives, there's
So you are still.
the second derivatives are non-negative. It means that the function is increasing. So it means that once it gets zero, I don't remember it. Once it gets
It's because you want to say, so when you say it is half space, you are already specifying what is the boundary.
yes.
You want to have it, say, if your half space is x1 greater than 0, then you have it only x1 square. You cannot have any other. Does it mean, because
It doesn't look like so straightforward. I'm thinking somewhere else. If we subtract x1 to power 2, let's say it's upper half space, if you subtract it, then it will be a harmonic function. Still, it will be 0. Yes, I think that's the solution. If you take a harmonic, if you take a u0 minus, I'm solving it for you, but that's okay. So if you take my u0 minus x1 to power 2 divided by 2, that can be a harmonic function. You're taking out the Laplacian, the source, Laplacian of u0 is 1. So this is going to be a harmonic function. They are both 0 here.
that's what
Yes, they are both 0 here. And they are both having quadratic growth. Okay. So if you take the derivative of this, that will have linear growth. Is that enough? A linear growth and...
No, what I mean is, what I'm saying is, to prove it is one dimensional in upper half space, maybe you don't require it to be the solution, but maybe the direction in which you will have it to be one dimensional will be determined by what half space you are in. That's what I'm saying.
Yeah, we can just rotate it.
That's fine. So say without loss of generality, if you assume it is x2 greater than 0, then we should be expecting only x2 direction, not.
But I don't see directly.
So that's what. So if you want to have it more specific, then of course you have to use comparison because you are having 0 boundary conditions, and that may not allow other directions to.
I don't see how without PD, I have, right now I don't see. But with PD, you subtract your x1 power 2 divided by 2 to get a harmonic function which vanishes twice on the boundary. But it's sort of analytic continuation thing, something like that. So the harmonic function which is 0 on the boundary, the gradient cannot be completely 0. It could be 0 at some lower dimensional sets, but not in a whole positive dimensional, whole lemma or even unique continuation properties.
We will see.
That's the easy way out.
Let's see.
Then you have to check if you really mean that it solves PD or not. But maybe yes. Convexity is a very strong property. Maybe that, I cannot right now think about it. So let's summarize what we have. So we took a local solution, we scaled it, and we looked at the blow up of this, and we obtained a homogeneous global solution, and which is either a polynomial or a half-space solution. That was the outcome. So either half-space solution, like with 0 and 0 here, or it's complete polynomial. Polynomials we don't like. So it means that when you do blow up, you have to assume from the beginning that the free boundary is in a way that you get actually the half-space solution, and not the polynomial. Because if you get polynomial, then you don't expect the free boundary to be smooth in the way you want to. So half-space is good. So you can start your machinery now, your theory, and or strategy of the proof around points when the blowouts are at stasis. And of course, you don't know if you blow up, it will be out of stasis or not. But there is another way of doing these things, which I think I'm going to do here. There are examples here when actual polynomials can appear, and polynomials can be of lower dimensional. Like in 3 dimension, we can get this one, which has a free boundary, which is just a line. We can have the polynomial x1 to power 2 divided by 2, which is positive here and positive here, and the free boundary is this. We can have polynomials when some of the monoids are missing, and then you will get lower dimensional free boundaries. Okay, so you see the richness here to study what kind of things you can get, and then go and look at singular points, but we will not do that. I did not do it here at least. So to obtain regularity, we'll restrict ourselves to the so-called good points. The good points will be those that really give you this one, give you half stasis. So we avoid cusps. And for that, what we will actually look at is, so we call a regular point, x0 is a regular point if the free boundary doesn't have a cusp. And it's a singular point if it has a cusp. So if you compute this, so that W here is the Weiss energy we had from the beginning, from yesterday, if you remember that. So let me go back to it so you can see. So the Weiss energy is this guy. So this is the Weiss. This is easier to look at this one because the scale version. You don't forget about it. You don't need this n plus 1, n plus 2, etc. If you look at the scale version of it, it's much easier. So if you look at the Weiss energy and we let r go to 0, and you can actually compute it, when r goes to 0, the integral actually becomes something like this. Since it's homogeneous, the blowout is homogeneous. Let's see. So what is the integral? The integral will be the gradient of, since it's homogeneous, I can take out r. Okay? So if I blow up, it will be homogeneous, so ignore r, because it really doesn't affect this homogeneous. So you have gradient of u to the power of 2 plus 2 times u. Integral over the polar rate is 1 minus 2 times u to the power of 2 over b1. Agree? This is the integral. I'm taking out r to be 1 because it really doesn't matter. If you put r here, it's homogeneous, you can take it out. Think x0 is 0. Homogeneous of degree 2, then r circle. Actually, wait. If you homogeneous, so if you integrate by part, this will be on the boundary, 2 times u, normal vector of u on the boundary, minus Laplacian of u. Agree? Or not? Integrate by part, and then u times Laplacian of u plus 2u. And this is just 1, our characteristic function, but the product, so it will be u times 1 basically. Characteristic of u is positive, so the whole thing is just u. And then we get minus 2u2 over the boundary. But the whole thing here will be just u. This guy disappears with this guy. Try to prove it.
You did this computation yesterday.
Did I?
Yeah.
Not completely. Now I'm saying it's homogeneous, so they cancel. There I didn't have homogeneity. Yeah, I just add them up.
Yes.
But I didn't use homogeneity. Now I'm using homogeneity. So it's homogeneous of degree 2, it means this guy and that guy are the same. So this will be 0. And you get, so yesterday you got something else. Today we get this one. Yesterday we got something else. You prime to power 2. Because I didn't use homogeneity. But today I'm using homogeneity, I'm getting this. Well, yesterday I differentiated. I'm not differentiating it. I'm computing W.
Okay, so W prime.
Yesterday was W prime. I'm not doing W prime. Today I'm just doing W.
So it's just integration by parts.
Yeah, W you can integrate by part, and this, if U is homogeneous of degree 2, these two cancel, and these two together will be U. That's the integral. And now you realize that if U is homogeneous polynomial of degree 2, so you see that if U is polynomial of degree 2, then you can actually do like this. So Laplacian of U is 1 basically everywhere. So this integral over B1, I want to replace it with a better polynomial. To take any polynomial, so this integral U over B1 is Laplacian of any polynomial P, which is 1. Any polynomial which is 1, Laplacian is 1, and then minus Laplacian of U times that polynomial, plus Laplacian of U, that polynomial. Okay, just compensate. And this is going to be 0. And this is 1 over B1. This is just integration by part. Integration by part, you go on the boundary, you use homogeneity of degree 2. P is homogeneous of degree 2. P2 homogeneous. Polynomials Laplacian is 1. You can actually replace it. Because on the boundary, it will be normal derivative. Normal derivative of this is degree 2, you're going to get 2 times P back. For this, you're going to get 2 times U back. It's going to be the same thing, and they disappear. So you get P. So for any, if you use polynomial, you're going to get this back all the time. And then, if you use half polynomial, another possibility is half polynomial, you're going to get half of this back. And now, because you can choose P to be specifically be 1/2 x1 to power 2, not with the plus here, complete polynomial. This is exactly twice. This is exactly twice when you take half polynomial by symmetry. So the energy, so Weiss energy at 1 for polynomial x1 plus to power 2 divided by 2 is actually, we call it alpha n divided by 2. That's exactly half of when you don't have this plus. And for the polynomial, it's actually alpha. Alpha n is a constant, written here, it's not important.
The notation for
It's already, yeah, for anyone, we have the same thing. So, this means that you really get a good grip on this by energy. Okay, so this means that at regular points, when you have spaces, blowups or half spaces, you get half the energy, the low energy. This is the first thing I told you about, the energies. Okay, now we're coming back to it. And at singular points, you get the double of that value. And this is good information. If you have a point when the energy is low or high, you can sort of tell you. You usually cannot say about high energies. If a point has high energy, because high energy might be several, here we have 2 of them, but there are examples in other type of free boundaries, you might get several values. So in low energy points, so look, when you get the lowest energy point, that's the best point. That's always a smooth surface. Okay? When you get high energy points, those are sort of isolated, not completely isolated, but they might be isolated from other singular points. Okay? They are connected to certain type of singular points by, let's say, you can think of something like this. Okay? A cusp, and then it goes like this. You see, this cusp is connected to other cusps of the same type. But it's not connected to lower order cusps when the energies might be higher. You don't have it here, but you see that it cannot be connected to them. So these are very interesting geometric thinking. You have to really think clearly to get all these things done. But the good news is, if you have lowest energy, those points are always good points. You have good regularity. Partly it has to do with, if you have a low energy, we'll soon see a little bit of that. If you have a lowest energy, then your functional value at that point is smallest value. When r goes to 0, think it as a function. When r goes to 0, you get the lowest value. Now, if you start with other points coming close to this, take any other point coming close to this, and compute your energy value asymptotically at that point. That energy cannot be larger than this value in the limit, because of upper semi-continuity of the energy. Okay? So because of upper semi-continuity, so this W is upper semi-continuous. We talked about lower semi-continuity of the functionals, if you remember. But now I'm saying, so this functional is lower semi-continuous in the variable U, but upper semi-continuous in the variable X. And yes, in X. And that's very important. So if you would define, so for each x0, you would, and this is just depend on x0, agree? And U is fixed. This depends only on x0, because I go in the limit. That's the function of x0. That function, I give you some exercise to prove, is upper semi-continuous in x0. So prove the function W, 0 plus U x0. So 0 plus is already fixed, U is fixed, x0 may vary. That's an upper semi-continuous function in x0. So if it's upper semi-continuous, you fix a point x0, and you come with other xj's close to this, the value in the limit must be larger than equal. So this value here is larger than equal whatever you're coming to, because it's upper semi-continuous, that's the definition of it. So it means energy values around this point for free boundaries are always less than equal to this. So it means the energy values close to a minimum point is always less than equal to this, so it has to be that, because there's no other values. So it means all points seems to be regular points. If you take a regular point, then anything around it is regular. Of course, the neighborhood depends on a lot of things. But there is a neighborhood that all free boundaries are smooth. And you see that already if you take a cone. So think of a cone. The vertex of the cone, that's a singular point. Think even two-dimensional cone, which is like a cylindrical. Okay, so you have this shape. So you see, if you take a smooth part of the cone, you cannot come with singular points close to this. It's always away. However, how close it is, it's still away. But if you take a singular point, you see that you can come with regular points close to it. You can come with other singular points close to it. But if you take a regular point, you cannot approach it with anything else but regular points. So that means that regular points are open sets. So regular points are relatively open in the free boundary setting. And it means that there is a neighborhood that all points are regular, and now you're in good shape. The question?
Sorry. The Sars theorem, it reminds me of Sars theorem.
Sars, I have to remind you about that.
Set of critical points of measures U or something.
Mm-hmm. Oh, I don't know. If it's connected, yeah. It's a different thing, yeah. Yeah, I think this is I usually find this the most beautiful part, in the sense that it carries so much information. It really carries a lot of information.
That's living with this sort of critical values.
Okay. So the conclusion is that if x0 is a regular point, then we have this balanced energy value, and this happens for half-space solutions. And you blow up, it has to be a half-space solution. There is no chance otherwise. So I will stop here, but let me just say what this means. It means that if you have a half-space solution, we zoom in, and then you take all this little ball, make it like V1, then your solution is very close to x1 plus, to power 2 divided by 2. So it means that your function u r, but your scale, is very close to this half space. In some norm, I'm taking the infinity, it's actually much better. I think you can make it C1 alpha. I think I'm going to use maybe C1 alpha very soon. So this norm is extremely close. Whatever epsilon you give me, I can choose an r, much smaller r, so that it's so flat that the difference is less than epsilon. Even in C1 alpha norm, actually, because convergence is actually C1 alpha. Okay? We're going to use this very soon. And this already actually reminds us of the problem with x2 minus sine something. We had this picture, and we tried to prove that the derivative is larger than equal. So this is the place where it helps us to get to that example and do the drill that we did with the example, but we're using PDEs here. I think we should take a break now and come back. Yes, that's good. So I send you. It's getting tougher. This is the beautiful part. These are all fresh research.